Welcome, Chemistry 1007. We got a final coming up, and so I'm trying to get all this material into your brains so you'll be great scientists, medical professionals. Anyhow, molecular geometry and bonding theories. That's what chapter 9 is. It's not really that hard. It's kind of fun, actually, I think, to look at these molecules and come up with Lewis structures. So really the first thing to do is kind of think about what geometrical structures are when we talk about small molecules, because that's what we're really looking at here is small molecules and covalent bonding. These are all nonmetals. So we're just looking at nonmetals. We're getting into organic chemistry. As you notice, we're just looking at the right-hand side of the periodic table for these atoms, which are bonded together and make up molecules. And we're later going to see how molecular orbitals are formed from the atomic orbitals that we learned about, such as s, p, d, and f, and principal energies 1, 2, 3, 4, and so on. Anyhow, molecular shapes, we can kind of build Lewis structures and get a good idea what kind of structure we have by connecting the atoms in the molecule we're given and come up with the shape. Lewis structures can be drawn as I showed previously. Remember my example in class of carbonate, the 2- anion, the polyatomic anion carbonate is a good place to start. Review that. If you don't understand Lewis structures, please review that before the final. Some of the common shapes with really 2 to 4 atoms is what we're talking about here. We will end up thinking about electron domain geometry, but we don't need to do that now. Let's just look at the structures. For example, we have an oxygen, a carbon, and an oxygen. That's completely linear. The A is the central atom, and the B2 are the peripheral atoms that are oxygen. A is carbon. We have SO2, but that's a little bit different, and that's AB2 as well, but it's bent. And what happens here is we're going to find out there's lone pairs of electrons on sulfur that change the geometry. Then we got SO3, not to be confused with SO3 2-. Those are two different molecules. This one has no charge. It's AB3, trigonoplanar, 120 degrees between each of these dihedral angles. If I were to tell you, well, what is a dihedral angle? We should start, we always need 3 atoms to get a dihedral angle. That could be 1. 2 is the central atom of the dihedral angle, and that is 3. So anytime we're talking about dihedral, we're talking about 3 atoms and the angle that they form. This one happens to be 180. This one here is roughly something about around 105 degrees. And then moving on to NF3, we have really 4 atoms involved here. We had nitrogen being A, the central atom. And we got to remember that the central atom is always the point of determining the geometry or the shape of the molecules, always from the perspective of the central atom. You cannot do this without identifying the central atom, because the central atom will tell you how the peripheral atoms are spaced relative to itself, and therefore you'll be able to get a geometry. So, of course, this is the central atom here, which is sulfur, and this sulfur is also the central atom, and carbon is the central atom here. Let's look at a very interesting one, ClF3, this molecule, very interesting. It's AB3, and it's called T-shaped because it's shaped like a T. So we're not really worried about all the electron domain geometries. We're just worried about the molecular shape. This will come in handy now as we move further. We do determine the shape of the molecule by how? Well, what makes this really simple is just looking at all of the electron domains. And here we don't really show any lone pairs. We don't show any lone pairs. Everything is connected to another atom. The central atom is connected to another atom, and so on, all of these. So we're kind of just looking at the overall shape. We're not even really totally considering the whole electron pair repulsion of the domains, but that's really how we're going to be able to figure this out. And we're going to have to name this so you understand. It's valence shell electron pair repulsion. And what this means is domains of electrons spread out as far as possible from each other as allowable in the physical space or the three-dimensional space that we have. And so they try the electron domains, which can be what? Electron domains can be two electrons in a bond, such as here. There's one electron domain, there's a second electron domain. This one has three electron domains. It has three bonds, so it has three electron domains from the valence shell. This one has four. This one and this one and this one and this one. We have four electron domains there to consider. For AB5, which is trigonal bipyramidal, it's a three-sided pyramid, but two of them put on top of each other at their bases. One is right side up, one is upside down, but we have 1, 2, 3, 4, 5 electron domains there. Then we have this really cool structure AB6 where we have the central atom here, and then we have 6 substituents attached to the central atom. Remember, the central atom is always the focal point to determine the electron domain geometry or the molecular domain geometry. Right now, we're just doing geometry. We'll get into it here in a second. But we have the bonds or the electrons, the pairs of electrons are considered an electron domain. So here's one electron domain. Here's two electron domains. There's three electron domains. There's four electron domains, and there's 5 electron domains. And finally, 6 electron domains. And when we have 6 electron domains, we have octahedral, which is a 4-sided pyramid attached to the base of an upside down pyramid that is 4-sided as well. So you got 2 4-sided objects, therefore giving you octahedral as the name. Electron domains. Okay, we already determined that these are pairs of electrons. This is a good way to count up electron domains. Now we're going to get a little more specific than we were previously. Here we have actually 4 electrons here, 2 electrons in each bond. Each line is worth 2 electrons. So we have really 4 electrons, but this is only 1 electron domain. Then we have what we know to be true from our past experience. We have 2 electrons in this bond, therefore another electron domain. And then here we have 2 electrons in this bond. We have a third electron domain. And remember, it's relative to the central atom. The central atom also has a lone pair of electrons, which is the first time we've seen that today. That's a 4th electron domain. So we have 4 electron domains. Only one of them are lone pairs. And so we can use this table to say how many electron groups are around A. Well, 3, 3, 4. We have 4 electron groups. Well, this is 4 around here. Now, okay, we have 2 that are 4. We could have 1 lone pair or 2 lone pairs. But here it says lone pairs on A. So we have to think about the central atom. There's only 1 lone pair on A. So that's this. So the electron domain geometry is going to be tetrahedral. If we ignore these lone pairs, it's going to end up being trigonoplanar. And so the electron domain geometry and the molecular geometry are not equal here. So I call electron domain geometry EDG. And in this case, it will not be equal to the molecular domain geometry. Okay. This double bond is only considered 1 electron domain because it's regionalized. All the electrons are trapped in this area. We go to this one. All the electrons are trapped in this area. All the electrons are trapped in this area. And then we have a lone pair, which is a little bit bigger than bonded electrons. It takes up a little bit more space than, so if I were to say lone pairs, takes up a little bit more space than just a bonded pair. We'll call that bonded pair, right? Bonded pair. So the electron domain geometry here does not equal the molecular domain geometry. Sometimes it does. If we were to take methane, and we'll just draw methane, and I'm going to tell you in advance, the carbon in methane has no lone pair electrons. There is no lone pair of electrons on the carbon they're all bonded electrons. Sorry to draw into that. I really picked a bad space, but we'll make it work. So we have this and we should always really start with the electron domain geometry, and then we should really go then to the molecular domain geometry. That's the easiest way. If we have to pick one way to do it, I say figure out what the electron domain geometry is, including the lone pairs and the bonded pairs, and then you ignore the lone pairs to get the molecular domain geometry. But use the electron domain geometry to figure out the overall geometry, and then go from there and ignore the lone pairs. And then minus the lone pairs as a group, right? Minus the lone pairs. And you will get your geometry. And they may be the same and they may be different. With methane, it's tetrahedral, tetrahedral. With methane, the electron, these are equal when we think about, they're equal for methane. They're not equal for this strange molecule, okay? So, we have some interesting things to look at here. Remember, I say the easiest thing to do is to start with the electron domain geometry, meaning that you figure out all the domains of electrons available, and then you figure out the structure, and then you ignore the lone pair of electrons, and you get the molecular domain geometry, which is exactly what they did here in this example here of PCl3, which is just like ammonia. NH3 does the same thing, although don't want you to confuse it. Phosphorus can actually hold d electrons and can have an expanded octet, but it doesn't here. Here it obeys the octet rule. It obeys the octet rule. So we could do the Lewis structure. The Lewis structure would tell us that phosphorus, for example, has 6 electrons, right? 6 electrons for phosphorus. And then chlorine we have 3 times 7. Or is it 3 times? Yeah, it's 3 times 7. And phosphorus, no, excuse me, phosphorus is 5. My fault. Phosphorus is 5. It's right below nitrogen. So we get 26. We get 5 plus 21. That equals 21. We get 26 electrons to place. And so you can draw the Lewis structure. And then from the Lewis structure, you can start spacing things out by electron domains. You space out the lone pair of electrons, and then the bonded pair of electrons, you space those out, and you get this electron domain geometry. Means you have to include the lone pair as a group, as a point group, and then you have to include all the atoms that have bonded electrons to the central atom. So you get tetrahedral, which is like a tripod, which is like methane. Okay, so methane and PCl3 have the same electron domain geometry, but they're going to have different molecular domain geometry. Methane will have tetrahedral as its molecular domain geometry as well, but not PCl3. PCl3, we're going to, for the molecular domain geometry, we ignore those lone pair electrons. They're gone, but the effect of them is not gone. And so now we end up with something that's trigonal because we have 1, 2, 3. We have nothing here at the top to consider, and it's pyramidal shape where it has 3 sides, so it's trigonal pyramidal. Interesting enough. Okay, so let's look at ClF3. We come up with the Lewis structure for ClF3. We place all the electrons. We end up with 2 lone pair of electrons, and we end up with this strange molecule that has 90-degree geometry. It has fluorine, chlorine, and fluorine. Remember, you need 3 atoms to get a bond angle, or at least 3 point groups. It could be a lone pair of electrons too. And it's 90 degrees apart. And these, however, though, are 120 degrees apart. So we have 2 angles in this strange, what they call here, if we look at the electron domain geometry, it's going to be trigonal bipyramidal, which means it's going to be a 3-sided pyramid with an upside down 3-sided pyramid. We're going to get trigonal bipyramidal for the electron domain geometry because we have to take into account these lone pairs of electrons, which are 120 degrees apart and also spaced away from the lone fluorine that's on the horizontal plane. But we have the axis is fluorine, the z-axis F and F, they are on the vertical axis. And if we go to the molecular domain geometry, what do we have to do? We have to ignore the lone pair electrons. We have to ignore those. They're no longer a point group. We don't look at them as a group at all. We just look at fluorine, 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 all attached to chlorine in the center. This is a very strange molecule, but it's kind of cool. And we get T-shaped. We get T-shaped, which is different. So again, the electron domain geometry is where we start. Once we have the electron domain geometry, we can ignore the lone pairs and figure out if the molecular domain geometry is the same or different. And we may have a new name for it, or it may be the same name, but in this case, it's different. Trigonal bipyramidal for electron domain geometry, and then it's T-shaped when we ignore those two lone pairs, and then we have the molecular domain geometry. Water is a really fun one. We really can't get around the fact that water is like one of the most important small molecules in the world. We can start with the Lewis structure. You could do the Lewis structure of water. Hydrogen is missing here. And what do you have to do to get the Lewis structure? You need to add up all the valence electrons. Do you add up all the valence electrons in the atoms? No, just the valence electrons. So oxygen has 6 and 2, each hydrogen has 1, so it's 2 times 1. We end up having to place 8 electrons around oxygen and hydrogen. And we can do that. We can see there's 2 electrons here, 2 electrons here, and then we have 2 lone pairs, which is another 4 electrons. So we want to get the electron domain geometry first. Remember, that's the easiest way. That's the easiest way. Get the electron domain geometry first, then you can figure the molecular geometry. So we place everything as far apart as possible. Everything's about 104 degrees apart for the this is a dihedral angle. Hydrogen, oxygen, hydrogen, you got to have 3 atoms or 3 point groups. You could have lone pair, oxygen and lone pair. That's about 104.42. So we get tetrahedral, which is like methane, but we have 2 less atoms in water than we have in methane. We have 2 extra hydrogens in methane, but a carbon at the center core and not oxygen. Now we go to the bent molecular geometry is what we get, but how did we get that? Well, we ignore the 2 domains of lone pairs. We ignore those, but we don't ignore their effect on the geometry. But now we don't consider these as we do not consider the lone pairs as point groups any longer. So instead of having 4 point groups as we do here, 1, 2, 3, 4, we only have 1, 2 groups. We ignore those as point groups, and now we have a bent molecular geometry. So again, EDG does not equal MDG in this case, right? Valence shell electron pair repulsion model. What do we have going on here? If we use balloons as an analogy, if we use balloons to help us do this, we can just look at the electron domains. We don't know if they're bonded or non-bonded. It doesn't matter here at first. Of course, this is always going to be the center. Here is always going to be the central atom. So we can have this is like 180 degrees. So this is probably going to be linear, where we have 2 electron domains, and then we have the situation where we end up having 1, 2, 3 electron domains, and they're going to be spaced apart. Trigonal planar, they're going to be 120 degrees apart. Then we can add a 4th balloon, and then we get 1, 2, 3, 4 balloons. And so the electron domain geometry here is going to have to be tetrahedral. But remember, we always start with the electron. We start with the Lewis structure, then we do the Lewis. We start with the Lewis structure. Lewis structure. We get that. Once we determine the Lewis structure, then we want to use VSEPR, valence shell electron pair repulsion, to get the electron domain geometry. So we know where all the electron domain geometry is around the central atom. We need to know the electron domains around the central atom, and then we can get the electron domain geometry from that. We apply VSEPR, and then we can ignore the lone pairs and come up with the molecular domain geometry. I think that's always the best strategy. What happens, domains of electrons always repulse each other, and they try to get as far away from each other as possible. If we have a double or a triple bond where we have 4 or even 6 electrons in a single or in a bond between two atoms, that's still only going to count as one electron domain. Even though there's more electrons in that domain, it's still regionalized to that area. So how does this work? Let's look at something that has 2 to 6 electron domains. And then we can, once we have the electron domains, it could be lone pairs or bonded pairs, right? So electron domains are everything. Remember, I say start from that instead of molecular. Don't determine the molecular domain geometry first. Determine the electron domain geometry first. So it's bonded pairs. So I'm going to call that BP, which is bonded pairs, not boiling point in this case. It's bonded pairs and lone pairs. That's what accounts for any electron. Each one of those can be an electron domain. We would have one bonded pair and one lone pair. We'd still have 2 electron domains. We could have 2 bonded pairs and 1 lone pair, and we'd have 3 electron domains. Okay, so remember, multiple bonds such as a double and a triple bond only count as 1 electron domain. We don't have to count it twice or 3 times. If we do, we're going to make a mistake in our initial determination of electron domain geometry, which is where we start. So if we have 2 number of electron domains, we know that those 2 domains are going to spread apart best by being 180 degrees apart. It's going to be linear, and the predicted bond angle is about 180 degrees. If we have 3 electron domains, doesn't matter if they're bonded pairs or lone pairs, they're going to spread roughly 120 degrees apart. We're going to get a trigonal planar structure. If we have 4 electron domains, they're going to spread apart. Each of the 4 domains of electrons are going to create a 109.5 dihedral angle with 4 different angles in that molecule, such as methane. That's tetrahedral, and that bond angle is around 109.5 to spread the electrons as far apart from each other so they don't repulse each other. Remember, electrons, when they're pushed together, they do what? They repulse. They're okay being paired up, but if you try to put pairs of electrons together, unless it's a stated double or a triple bond, it doesn't work so well. Allowable energy levels, right? Some of this is memorization, some of it is theory. We have 5 electron domains. We have 1, 2, 3, 4, 5. We get this unique trigonal bipyramidal structure with respect to the EDG, and it spreads out with 190 degrees from here, the central atom, and here. So if we go along these axes, everything's 90 degrees apart. But if we go along the horizontal axis, everything spreads roughly 120 degrees apart. And it works out nicely to create the maximum or the minimum amount of repulsion between electron domains. How many electron domains are there? 5. What is the structure with respect to the electron domains? Trigonal bipyramidal. Then we have 6 electron domains. We get into this really cool structure, but let's count it. Here's electron domain 1, electron domain 2. Then on the horizontal or flat planar, we have the 3rd, 4th, 5th, and 6th electron domain. And in this one, everything is 90 degrees apart, which makes sense. Everything is as far away as possible from each other as can be expected to minimize repulsion, valence shell electron pair repulsion. You want to minimize electron repulsion because you push 2 pairs of electrons together, the energy gets raised up to the moon, and it doesn't like that, and it wants to relieve the energy by getting away from the other electrons. It doesn't like electrons, right? This is octahedral because we have a pyramid with 4 sides on top, and then we have an upside down pyramid at the base with 4 sides on bottom. And so we have 8-sided object which is where octa comes from, and all the angles are 90 degrees. We could also call these electron domains coordination numbers. This is very important in Gen Chem 2 when we get into complex ion formation, which is really cool stuff. Okay, so VSEPR, determine the molecular shape. Well, first, know what the molecular formula is, draw out the Lewis structure, determine the electron domain geometry, and then determine the molecular geometry last by eliminating these lone pairs. And you get the electron domain geometry is different from the molecular geometry. The electron domain geometry here is tetrahedral. It's tetrahedral, right? And this one is the molecular domain geometry. The molecular geometry or molecular domain geometry is trigonopyramidal when we ignore the lone pair as a point group. We ignore the lone pair for the molecular geometry. Draw the best Lewis structure you can, determine the electron domain geometry, arrange these bonded atoms so they follow VSEPR and they're spread apart. All the electron domains are spread apart as far apart as possible. So you use VSEPR here really at this point. And then to get the molecular geometry, you ignore the lone pairs. So linear, we've looked at this before, but we haven't really thought about the non-bonding domains. We know previously that we have 2 bonding domains of electrons, which works out to be linear with this respect to the central atom. Maybe there's 3 atoms involved here. There are no lone pairs here, so we have 0 non-bonding pairs. So the electron domain geometry is going to be the same as the molecular geometry. They're both linear. And we will talk about what happens when we have 3 electron domains and maybe only 2 of them are bonded pairs and we have a lone pair. We have 3 electron domains or 4 electron domains and one of them is a lone pair and the rest are bonded pair. So we'll find out different combinations will change. The electron domain geometry can vary with the molecular domain geometry, as we've seen. Have a great day. We'll be back soon with more of Chapter 9. Thank you, Chemistry 1007, for listening.